Welcome once again to yet another mathematics session in this O-level series. Throughout the course of the few weeks, we have looked at a host of concepts and theorems and topics ranging from indices to logarithms to variations as well as simultaneous equations. More importantly, last week we started on a concept revolving around triangles, or more importantly, three-sided shapes. We call that concept the concept of trigonometry, right? We consider that first and foremost, for a three-sided shape, which we normally call a triangle, that means, yes, it will have a side, another side, and a third side, three sides, and it will also have three angles. Now, for this triangle, whenever we now do in-depth studies into what the triangle is, the types of triangles that exist, the classifications of those triangles, then we say we are studying the concept of trigonometry. So we began the concept of trigonometry the last class, and we looked at various things about it. One of the most important things we considered in trigonometry was the fact that you could classify triangles based on their sides and based on their angles. We said that if you classified the triangles based on the angles, then you would have acute angle triangles. That means all the angles within this triangle is less than 90 degrees. You'll have right angle triangle. That means at least one of the angle is exactly 90 degrees, something like this. And you usually denote that 90-degree angle with like a square shape. And then you have the obtuse angle triangle, which means that at least one of the angles within that triangle is having an angle greater than 90 degrees. For instance, something like this, where this is obtuse. So it's this time around we are saying this angle is greater than 90 degrees, right? This is classification of triangles based on the angles. We also talked about the fact that you can also classify triangles based on the sides. We looked at the equilateral triangle, where all the sides are equal. In fact, we generalized to now say that if all the sides are equal, that also means that all the angles are equal, right, for the equilateral triangle. And of course, the angles are exactly 60 degrees on each side. Then you have the isosceles triangle where two of the sides are equal. So if two of the sides are equal, that means there would also be two of the triangles that would also be equal. We looked at that. And then we also considered the scaling triangle where none of the sides are equal. But that was not our major focus. Our major focus was to discover the various rules that govern calculations or analysis into the concept of trigonometry. And we considered quite a few of them. We started off with the Pythagoras theorem, where we considered the relationship that existed between the sides. We said by the theorem that the square of the hypotenuse side, which was the side facing the 90-degree angle, is equal to the square of the other two sides. That concept of Pythagoras theorem was used to lead us into yet another important trigonometric rule, which we call the trigonometric ratio, or popularly known as the SOHCAHTOA. This time around, we are now utilizing the Pythagoras theorem to check the relationship between the sides with respect to one particular angle. We found out that the sine of an angle was equal to the opposite side divided by the hypotenuse. The cosine of an angle was equal to the adjacent side divided by the hypotenuse, and then the tangent of the angle was equal to the opposite side divided by the adjacent side. We then move forward to extend this concept of the trigonometric ratio into concepts revolving around trigonometric identities. We said that with the Pythagoras theorem, we could regenerate a relationship this time around between the trigonometric ratios. So the relationship between the sine and the cosine is the fact that the square of the sine plus the square of the cosine is always equal to 1. We also looked at different other properties. For instance, the square of the tangent plus 1 is equal to the square of the secant, right? And so on and so forth. I hope you were able to catch up on all those concepts as we mentioned, and also try to take questions from them. Today, we will be continuing along that line. Of course, all of those are not the only things we can do with the concept of trigonometry. That is, with the host of knowledge that is available for triangles, that can surely not be the only thing we can do on them. Today, we'll be looking at several other rules that exist for triangles, as well as this time around how they apply to different other plane shapes. Do not forget that the triangle is a plane shape. What do we call a plane shape? A two-dimensional shape is called a plane shape. Basically, any shape that you can draw on a piece of paper is a plane shape. So your triangle, your square, your rectangle, your circle, your kite, your rhombus, your parallelograms, those are plane shapes. However, anyone in which if you were to construct them, a plain paper would not be enough. We call those ones the solid shapes. So your example is your cube, like your Maggi cube, for instance. Your cuboid, like your NOR cube, for instance, right? Those are solid shapes. Another good example is your big Gino tomato paste cylinder, because that's a cylinder now. You also have your custard container. That's also a cylinder. Those are solid shapes, because you cannot obviously draw a matches box or a matchbox on a piece of paper. Yes, you can construct it by doing something like this, but yeah, this is just you trying to adapt it onto the plane shape. However, in real life, once you hold your matchbox, you already know that, yeah, this is not something that is meant to be put on a piece of paper. So that's why we have solid shapes. We also call them three-dimensional shapes. However, for today, we are now looking at the relationship that triangles would now have with other plane shapes, most especially the circle, right? The circle is one major shape in the concept of mathematics. There are a whole lot of concepts that are hidden within the circle. Immediately after this class, as in our next class, God willing, we would be taking in-depth studies into the concept of the circle, which is obviously the next plane shape we are going to be considering. And then we will now look at the different relationships or characteristics that the circle have. However, to introduce us to the concept of the circle, today we'll be looking at the relationship the triangle shares with the circle. So let's begin our study. Now, so of course we are still on trigonometric rules. So today we will not only just look at the relationship triangles share with the circle, we will also look at some other rules that exist for triangles and how we apply them. Some of those rules, of course, include the sine rule and, of course, the cosine rule. And then we'll look at how they are formed. Now, let us begin our class for today. Do not forget, for a circle, it's a plane shape that is obviously in a circular format. It has a center, and more importantly, it has a radius, right? Now, of course, if you extend the radius directly on the opposite side, then you would say you have yourself a diameter, right? The two of the radius gives you the diameter, right? So you have the radius here, and together they form the diameter. The diameter is not yet our concern as of now. Now, what happens when you consider the two radius this time around not directly opposite each other, right? If this is the case, you would agree with me. Of course, you should know that the angle at a point is equal to 360 degrees, right? This angle at a point is also the same thing as you say an angle in a circle, right? Because do not forget that the circle starts at that point, right? And then you draw the circumference around that point. So you say the angle at a point is 360 degrees. Remember that. Now, the moment we draw two radii from that center, what do you notice? A new angle is formed that is going to be a portion of this 360 degrees, right? So this is a portion, and of course, what you have here is another portion. Summing this side and this one together will definitely give you 360 degrees. That is fine. However, for this one, you would also notice that this portion here, if I extend from the tip of the first radius to the tip of the second radius, if I extend a straight line from tip to tip, what do you notice? Now I have myself a triangle. Let's name this A, B, and C for center. Right? What do you notice? From the two radius, I now have myself a third line, and the combination of these 3 points is forming me a triangle. What does that tell you? It tells you that within your circle, you can, yes, completely form a triangle within it. In fact, this third line, right? This third line that complements the first radius, obviously we know this is the radius because it comes from the center to the circumference. We also know that this is also the radius because it comes from the center to the circumference. Now, the third line that complements the two radii and joins their endpoints together, this third line is what we refer to as the chord. Are we together? And the moment we join the two radii together with this chord, a triangle will be formed in their midst. A triangle will be formed in their midst. What does that now immediately tell you? It tells you that every single concept that exists for triangles will be satisfied within this shape, right? Which means we can use this concept of a triangle to in fact find the value of the chord, which is what we call the length of the chord, right? So to find the length of the chord, we utilize the concept of the triangle and the calculations based on the triangle. We can also in fact find the value of theta within this chord or within this triangle ABC. Yes, because we can always find the angle within a triangle. We can also even find the value of R, which is obviously also a point or a side of the triangle. So you see that there are a lot of concepts relating to the triangle that can be utilized within the circle itself. This is a very, very important relationship that we have to bring out. Now, let us give ourselves the hint as regards to how we solve them, and then we will now take several questions on solving length of chords, and then we will now move on to the other trigonometric rules. Now, this time around, the triangle looks to be at the side, so let's do a circle. Let's do another circle, this time around where the triangle will face down. So it looks more like a triangle. So we have ourselves theta here. This is the radius. This is another radius. It's A, B, C. Now, what is the very first thing you notice? The two sides or two of its sides are equal, right? Because two of the sides are made up of radiuses. Now, do not forget, when we classified and categorized triangles, we said that when you have a triangle where two sides are equal, then that triangle is called an isosceles triangle. Where two sides are equal, you have yourself an isosceles triangle. That is very, very important to note. Now, what does that mean? And if we talk about the characteristics of the isosceles triangle, you remember that whenever the two sides are equal, it also means that the two angles that are directly opposite those sides will obviously be equal, which means this is the angle directly opposite the first R. If we call this angle R, this is the second angle opposite here. This will also be R, right? So as the sides are equal, as the two sides are equal, because they are both the radiuses obviously, the two angles opposite them will also be equal. This is using the characteristics of the isosceles triangle, which is a triangle where two sides and two angles are equal. Keep that in mind. Now, that is just by the way. Another most important characteristics that also assist us to solve is, from this isosceles triangle, we can create a right angle triangle or two right angle triangles from it. By perpendicularly bisecting this isosceles triangle into two equal parts, what happens? That means from the top angle, perpendicularly bisect the triangle. What this means is that immediately the angle at the top will split into two equal halves. So if we said the angle at the top was probably theta, then this place will be theta over 2. This place will also be theta over 2. So whatever the angle is that is subtended at the top, or that is held at the top, that is at the center, the moment you bisect that triangle equally into two equal parts, the angle at the top will also bisect into two equal angles. I hope that is clear. Now, that is not the only characteristic that comes out. The moment you have bisected perpendicularly, we also notice that this angle here splits into two right angles. That is 90 degrees on this side, 90 degrees on this side. So now we have ourselves a first right angle triangle, and then we also have ourselves a second right angle triangle. What this means is that whenever you are able to construct a triangle within a circle, then you are not only going to be able to construct that triangle, you will also be able to bisect that triangle perpendicularly in order to create two right angles triangle. The moment we are now able to extract two right angle triangles, then it means that all the rules that we generated for right angle triangles will definitely work. Talking about the Pythagoras theorem, the trigonometric ratio, and of course, the trigonometric identity. Do not forget that this third line, AB, right, is what we refer to as the chord. So what it also means is that the moment we perpendicularly bisected this triangle into two equal parts, that means we have also broken the chord into two equal parts as well. So if we call this part X, this is also going to be what? Part X, right? Because they are now in two equal parts. By extension, it then immediately follows that if we construct this right angle triangle and then find the value of X, to now find the length of the chord, all we just have to do is add X to itself, or we say we multiply X by 2. That is the process of generating the length of a chord using the rules and identities generated by trigonometry, or by the study of the concept of the triangle. Now that we have given ourselves a good breakdown into what we will be discussing in the next few minutes, let's now take practical questions to clarify these things further, right? So based on what we have said, that if you have any points that is not clear, you can let me know, right? But in the absence of that, we will proceed immediately towards picking questions on concepts like this. We would also pick questions relating to the first part of trigonometric rules that we did last week, so that we would ensure that we have a complete knowledge of what we have done so far as regards the concept of trigonometric ratios before we then pick other new concepts. Let us start off with this question. Calculate the length of the chord between two radii of a circle with an angle subtended at 60 degrees with radius 10 meters. This is what we need to calculate. The very first thing is, let's try as much as possible to, of course, prepare this in a diagram as clearly as possible. Of course, whenever you utilize diagrams, what you notice is that it makes it easy for you to identify what exactly you are looking for, and then also piece out the steps you need to go through in order to get your solution. So now this is our circle. It has obviously a center. Now what we know is that it's obviously between two radii with an angle subtended at 60 degrees. What that means is that between the two radii, the angle is 60 degrees. That means between this first radius and the second radius, the angle there, this theta, is equal to 60 degrees. So that is what we need to construct. So I'll just, of course, showcase it as clearly as possible. That means the angle here is 60 degrees, right? Now, the radius in itself is 10 meters. This is also 10 meters. Now, we have to calculate the length of the chord. Where is the chord? The chord is from the edge of the first radius to the edge of the second radius. Let's call this L. So this is the information we have been given in the question. We have been given the angle subtended at the center. We have also been given the value of the radius, and then we have been told to calculate the length. Now that you have this, of course, you can decide to extract the triangle from the circle so that you have much more space to work. So if I decide to extract this triangle, I'm simply saying I have a triangle of this form, right? This is 60 degrees. This side is 10 meters. This side is 10 meters. And I'm to look for L. Now, this is what we have. Now, based on what we have learned so far, we can perpendicularly bisect this isosceles triangle into two right angle triangles. So if I break this triangle at the middle into two right angle triangles, what will I have? First off, the angle at the top, which is 60 degrees, will then break into 60 divided by 2. That's 2 of it, right? So on this side, I will have 30 degrees, and then on this side, I will also have 30 degrees. That is the very first step that has to be done. I have to be able to bisect this isosceles triangle into two parts. By extension, it also means that in this chord, which is obviously the baseline, it splits into two equal parts. Let's call each part x, right? So what that means is that for me to be able to find the length of the chord will be equal to the first x plus the second x, which of course you can also call 2x, right? So what do I do? Another thing you can also notice is that the right angle triangle on the left side is obviously the same thing as the right angle triangle on the right side, right? They are exactly the same thing, which means whatever value of x you calculate on this side is going to be the same value of x on this side. So you should not be worrying about, okay, which one should I use? Any one of them is fine. All together. Now I need to find the value of x first and foremost. Do not forget that in generating the value of x, we have the side which is 10 meters. Now note the position of 10. 10 is directly opposite the 90-degree angle. Remember we said the 90-degree angle is always signified by that square shaped mark. So 10 meters is directly opposite the 90-degree angle. So it means that this 10-meter side is our hypotenuse side. Now the 30-degree angle that we know is on the top, which means the side opposite that 30-degree angle, which is the acute angle, becomes our opposite. And then the last side, which is this perpendicular line, becomes our adjacent. We have discussed how you can break down your triangle into opposite, adjacent, hypotenuse. For any triangle you have, whenever you have the square shape, the side opposite it is the hypotenuse. Whenever you have your acute angle, the side opposite it is your opposite side, and then whatever is left is your adjacent. So use that same concept for this. In that case, it means this is the opposite side, this is the hypotenuse. I know the angle. From our trigonometric ratio, SOHCAHTOA precisely, we know that sine theta is equal to opposite over hypotenuse. We are looking for the opposite side. We have the hypotenuse, we have theta, which in this case is 30 degrees. What does that mean? It just means that sine 30 is equal to x over 10, right? Let's make x over the formula. That means that x